Welcome to the first CG&T seminar of the term. Our first talk is by Peter Zeman from the Department of Algebra at the Charles University, and he will talk about NPA hierarchy for quantum isomorphism and homomorphism indistinguishability. Take it away, Peter.
Yes, thank you for the introduction. So this work was done during my postdoc at the Technical University of Denmark with David Robertson. And so this postdoc was about at the interface of combinatorics, quantum information theory, and quantum groups. So we had some people there. So also Jossa, who is sitting there and answered all the questions. He was also part of that, and we did some work on quantum automorphism groups of graphs and this quantum isomorphism that was introduced. And so in particular, kind of like the idea for this paper. So originally David with his wife Laura, they did this quite seminal result about quantum isomorphism and its connection to combinatorics, which I will talk about. So the idea for this particular project came from this. So Prem, he is now finishing his PhD with David, and he was taking a course on convex optimization. And part of the assignment, they were supposed to study some topic, and this NPA hierarchy, it's kind of a semi-definite programming hierarchy that is used quite extensively in quantum information theory. So he decided to study this, and then there was this idea like, why don't we just apply it to quantum isomorphism? And this is what came out of it. So it's sometimes good to attend courses. It brings some benefit. Okay, and so maybe can we remove this somehow? Okay. Yeah. So the central notion here is like I will start from the motivation in combinatorics. So the graph isomorphism of graphs is just a bijection between the vertex sets of two graphs, such that it preserves adjacencies and non-adjacencies. Okay. So for example, these two graphs are clearly isomorphic, and a related notion is that of a homomorphism of graphs, which is just a mapping between the vertex sets of graphs, which only is required to preserve adjacencies. So, for example, there is a homomorphism between the 7 cycle and 5 cycle, and it is depicted here by the colors. So these two vertices can map on one vertex. These two can map here. So this is a homomorphism of graphs, and these two notions are brought together by the Lovaas theorem, which says that two graphs are isomorphic if and only if they have the same homomorphism counts from every other graph. So for every other graph F, so this denotes the number of homomorphisms from F to G. So if the homomorphism counts are the same if and only if the graphs are isomorphic. So this is the Lovaas theorem, and this naturally leads to the notion of homomorphism indistinguishability. So if you restrict the graphs F to be from some specific class of graphs, then you can talk about homomorphism indistinguishability over that class of graphs. So it's denoted like this with the class of graphs in the subscript. So now you say that two graphs are homomorphism indistinguishable over this class of graphs if you have the same homomorphism counts, but now you only go through the graphs in that class. And now in combinatorics, people study this. This gives you some equivalence on graphs, and which will be, of course, weaker than in general than the isomorphism, and people study this equivalence. So an interesting question is if you take this class of graphs to be some natural class of graphs, then what happens? What is this equivalence here? So here is some table of known stuff. So for example, if you take the class to be the all graphs, then you just have the isomorphism, and that's the Lovaas theorem. So if you take them to be the cycles, then you get something called cospectrality, which means that the adjacency matrices of the graphs have the same multisets of eigenvalues. So it's kind of similarity between them. Then cycles and paths, you get cospectrality and cospectral complements. And then when you restrict to trees, then you get so-called fractional isomorphism. I will mention that later to get some intuition like what it is actually. But it's like we can think of it like a very relaxed version of isomorphism. And then if you, for example, this tree width, whatever that is, I'm not going to define it, but this tree width is like kind of like a graph parameter which tells you how close is a graph to a tree. So for example, trees have tree width 1 and so on. So it gives you some kind of measure how close a graph is to a tree. And then you have some corresponding notion of equivalence, which is indistinguishability by some k-dimensional Weisser-Lehmann algorithm, whatever that is. But you have a lot of these examples. And now, from the combinatorics point of view, if you look at the list of these classes, a natural question is, okay, what is the relation for planar graphs? Because once you already consider trees, cycles, paths, and so on, then the next natural class is planar graphs. This is a class of graphs that appears a lot in graph theory in various kinds of applications, algorithms, and everything. So, and this is the surprising connection with the quantum information theory, that the planar graphs, the homomorphism indistinguishability over planar graphs is actually quantum isomorphism. And so if you're just interested, for example, in combinatorics, you naturally have to arrive to this notion. And what we do in this work is that we also actually reprove this result. And we do somewhat more because for this quantum isomorphism, we can consider some semi-definite programming relaxations, which is like a series of semi-definite programs. And for each of these semi-definite program, like the feasibility of each of these programs in this level gives you another equivalence notion, which is kind of weaker than the quantum isomorphism. And we define a class of graphs PK, which is a subclass of planar graphs. And the homomorphism indistinguishability over this class will be equivalent to this relaxed notion of quantum isomorphism. And there is some convergence properties. There is a convergence property of this hierarchy, which actually then helps us to recover the original result of Manchinska-Robertson. So actually, the original proof relies heavily on quantum groups. And in this further work, we can avoid that. We can basically, it turns out we can just use elementary linear algebra to prove this. So it has some benefits. So it's a more elementary proof which avoids quantum groups. I don't know, maybe it's a benefit for someone, maybe not. And then it has some algorithmic consequences as well. So I have to say that this isomorphism is very interesting from the algorithmic point of view in theoretical computer science. And the quantum isomorphism is undecidable. So there is no algorithm that can decide whether two graphs are quantum isomorphic or not. But with this, we can, for each of these approximation of quantum isomorphism, we actually can get some algorithm that can do it. Okay, so this is like the high-level idea of the whole result. So some kth level of the NPA hierarchy for the graph isomorphism game, which I will define, is feasible if and only if there is this level k quantum isomorphism map from G to H, which is like the relaxed version of the quantum isomorphism. And this is if and only if the graphs are homomorphism indistinguishable over this class of graphs PK. So let's first recall the quantum isomorphism. So it goes to quantum information theory, to the concept of non-local games, also known as Bell games or Bell inequalities in the physics literature. And in these non-local games, we have a two-player cooperative game between where Alice and Bob want to play against referee. And let's just see. So in this game, we have finite sets of questions and finite sets of answers, and we have some winning predicates. So so referee sends question X to Alice and a question Y to Bob, according to some probability distribution, let's say. And then Alice and Bob respond. Alice responds with answer A, and Bob responds with answer B. And they only play one round. They decide on strategy beforehand, and they cannot communicate once the game starts. So these are important aspects. And so the winning predicate, basically, referee uses it to determine whether Alice and Bob win. Okay, so this is like the most famous example of a non-local game for which there was, for like experimentally verifying this, was a Nobel Prize in 2022. So here the questions and answers are just 0 and 1. So here should be B. So this is just uniform, and so the players win if the XOR of the answers is equal to the end of the questions, and they lose if it's not the case. You can, okay, so this is the game. This is the general framework. We have some questions and answers and some winning predicate. And this is very general framework, so you can describe a lot of things using this game. So now what can the players do? They have some kind of possible strategies what they can do. There are many possible strategies. We will only mention a few. So the most basic one is just a deterministic strategy where the players have to play according some functions. So then the classical value of the game would be the maximum over all possible such functions, and then this sum. So this is the probability of getting the questions x, y, and whether they win or not is determined deterministically. Okay, and then we have a quantum player. So the idea is that the quantum players share some state, and they can use the state to maybe fool the referee, if you will. So in this case, both Alice and Bob have their sets of measurements. So for each question, Alice has a full set of measurement operators. So measurement operators is just a bunch of matrices. So if you fix X, you get, for each answer, you get a bunch of you get a matrix. So you have a bunch of matrices that have to sum up to the identity, and they are positive semi-definite. And so if Alice gets a question, she uses those measurement operators to get an answer, and likewise Bob. So applying a measurement actually is done by adding here a tensor with an identity, and then Alice measures her part of the state, and Bob measures his part of the state. and they get some answers which they use to respond. So here, this comes from some basic axioms of quantum theory, that the probability, so this is, we don't need to go into those axioms, it's just the probability that they both respond with some particular A and B is given by this kind of formula. So here we have the tensor product of their measurement operators, and here it's sandwiched by this shared state phi. So this is somehow, we can think of this for the purpose of this talk just as an axiom, that this is the probability with which they answer A and B given X and Y. And then similarly, you have a quantum value of the game, which is basically a supremum of this expression over all possible strategies. So for example, as we have seen the CHSH game, it's not difficult to work out that the classical value of the game will be 3/4. And it's not obvious, but one can prove that the quantum value is this, so which is strictly larger than 3/4. So this sort of like proves the power of entanglement, that sharing this entangled state gives you a possibility to fool the referee in some sense. So you can achieve a better value of the game. Right, and okay, so important for us will be actually the graph isomorphism game. So here again, it's the same framework. So Alice and Bob want to convince a referee that two graphs are isomorphic. So we will be assuming that the graphs have the same number of vertices, and this is the same idea, right? So Alice gets so the question, so we have two graphs, and the questions are from one graph, and the answers will be from the second graph. So Alice gets a question G, which is a vertex of a graph G. Bob gets a question G prime, which is also a vertex, and they both respond with the vertices from the other graph, H and H prime. And when do they win? What is the winning condition? Is that so the relation between the answered vertices should be the same as the relation between the question vertices. So what does it mean? Is that it just means that if the original vertices were adjacent, then they to win they should respond with adjacent vertices. If they were non-adjacent, they should respond with non-adjacent vertices, and if they are equal, they should respond with the same vertex. So it is not hard to see that two graphs are isomorphic if and only if the classical players can win the game with probability 1. So this is what we call a perfect strategy, when you can win with a probability 1. When you have a strategy that will always win. Okay, so because if they are isomorphic, they will just play according to the isomorphism, and the other implication is also not that hard to see. We use this to define a quantum isomorphism. So you just say that two graphs are quantum isomorphic if quantum players can win the graph isomorphism game. Now, there is a subtlety here that I defined quantum strategies as the players sharing some state on some tensor product of Hilbert spaces, which you can do, of course, but this notion would not give you the homomorphism indistinguishability result with planar graphs. So there is actually a more general framework for quantum strategies, where instead of sharing a state on a tensor product of Hilbert spaces, they share a state on just one Hilbert space. And now here the Hilbert space is allowed to be infinite dimensional. And so this is called the commuting operator strategy. It's a more general framework than the finite dimensional tensor product strategy. And this is actually a different notion in the sense that you can distinguish in case of you can separate those two strategies. So so here again you have some measurement operators on which are bounded operators on some Hilbert space on this Hilbert space. And Alice has these operators and she performs these measurements and she obtains some outcome H, which she uses to respond. And similarly, Bob has the measurement operators. And so the condition, so the condition here is that, so because we just have one Hilbert space, not a tensor product of two Hilbert spaces. So here the condition is that the operator of Alice should commute with operator of Bob. That's why it's called a commuting operator strategy. So it's not difficult to see that the finite dimensional tensor product strategy that I mentioned before is actually a special case of this, because if you take the measurement operators and just add a tensor with identity and also with Bob, then you actually get something that will commute. So here, again, we can take this as an axiom that the probability that they will answer with vertices H and H prime is actually given by this formula here. So here is now the product is no longer tensor product because everything is on one Hilbert space. So okay, so this is the quantum isomorphism. So if two players have this quantum strategy, then we say that the graphs are QC isomorphic. This denotes actually this more general framework, the QC. So here are the examples of graphs that are not isomorphic but are quantum isomorphic. So I will just prove by picture. You can see it. They are not isomorphic. Clearly, yeah. They are not isomorphic, but they are quantum isomorphic. So the construction comes from linear system games, which I will not go into. But actually, this is where also the undecidability comes from. So you can reduce the word problem to linear system, to satisfiability of linear system games, and then you can reduce this to quantum isomorphism. So actually, this is where the undecidability comes from.
A short remark, if anyone's ever heard of arithmetic square, this is a graph version. If you've not heard of it.
Yep. Yeah. Oh, maybe I can take this opportunity to advertise my course on quantum information theory, which is on Fridays at Caroline, the seminar room of Department of Algebra at 12:20. So there has been one lecture, but only the basic stuff, which are basically already explained here. So if you're interested, you can come. We'll also talk a little bit about this Mermin-Paris magic square game there. Okay, so we have seen in the pre-seminar talk this quantum permutation matrix. So we already seen this. So it's basically some matrix where the elements are, or the entries are the elements of some sister algebra satisfying this kind of conditions. So the row sums and projections and column sums. And so Lupini, Manchinska, Robertson, they proved that two graphs are quantum isomorphic if and only if there exists a quantum permutation matrix that satisfies this kind of relation. And this is very similar to these relations for isomorphism. So for isomorphism, we just have a permutation matrix. And for this fractional isomorphism that I mentioned in the beginning, which is equivalent to homomorphism indistinguishability over trees, we have a doubly stochastic matrix. So homomorphism indistinguishability over trees or fractional isomorphism is equivalent to this kind of relation being satisfied for a doubly stochastic matrix. So these are adjacency. So doubly stochastic matrix is row sums and column sums should be to 1, so sum up to 1. And so you can have, for example, like rational numbers in there. So it's kind of like a, sorry? Non-negative, of course, yeah. So it's kind of like a relaxation of permutation matrix as well. So yeah. Okay, so this is one way to think about it. Okay, so now we will go towards the result. So there is a lot of pictures here, so I hope this. I think if there is one part to take from it is this about bilabeled graphs, because this is like a technique for proving some homomorphism indistinguishability results that appears in more papers. So I guess this part will be a lot of pictures. It's a main takeaway, I would say. So we need this notion of a KK bilabeled graph, which is just you take a graph F and basically just like distinguish two vectors of length k of vertices, and that's it. So you just it's just a graph with some vector u of k vertices and vector v of k vertices, which are distinguished somehow. So it could be, and they can be repeated. So it could be like a complete graph on 4 vertices, and the first vector could be 1, 2, and the second could be just 2, 2. So let's just see a visualization. So here is this graph. So you have K4, and then we use the following way to visualize it. So so here we say like this: 1 and 2 are the input vertices. For the reasons it will be obvious. So we draw 1. So we draw like this kind of wire here, and then the 2 is the second label, so we draw it here. So we draw it from the top to bottom, and similarly, so here we have 2, 2. So the first one is drawn as the first, and the second one is drawn below it. So, but both of them are 2, so it's like this. So you just draw the labels from top to bottom and connect them with the respective vertices. So this bilabeled graph is planar if you can draw it without crossings. So this is not a planar drawing because you have the crossings here. So you also don't want to cross these wires. Okay, so now a notion of homomorphism counting matrices. So now we have a bilabeled graph. So graph G and a graph F, which has these 2 vectors. And now this is slightly technical. So the homomorphism counting matrix to correspond homomorphism counting matrix F of like this G is some arbitrary graph, right? And this F is our KK bilabeled graph. So this will be indexed by the following entries, or strings. So the first part of the index of the matrix is k vertices, and the second part is k vertices. So it's indexed by k tuples of vertices, and the entry at this point, so G1 to GK, G1 prime to GK prime. So what is in this particular entry is the following. So it's the number. So this is a cardinality of this set. So it's the number of homomorphisms from this graph F to graph G, such that this input vertex, this label UI, so which comes from this vector, gets mapped to the eth element of the string here. And similarly, the jth label from this vector here gets mapped to the jth element of this string here. So let's, and so in particular, the number of homomorphisms from F to G will be the sum of all these entries. This is what we want. So this matrix will capture the number of all homomorphisms from F to G, and in its entry. So let's do a simple exercise. So this is our graph A, which is just K2 with one input label and one output label. So you draw it like this. And the question is, what is the corresponding homomorphism counting matrix? So if you have seen it, don't answer. But it's just like, let's do this simple exercise. So, right, so G is an arbitrary graph, and A of G is the homomorphism counting matrix for this graph G. So this is 1, 1 bilabeled graph. And what we want is in the entry corresponding to G prime, we want the number of homomorphisms from this graph A to G. So what is this matrix? The hint is in the notation. Yeah. I heard something. Sorry?
Yes.
Yeah, it's the adjacency. It's exactly the adjacency matrix. So there is 1 if G and G prime is an edge, because then you have the homomorphism, and there is 0 otherwise. So this particular A of G will be the adjacency matrix of a graph, which is a weird way to represent the adjacency matrix, of course, but yeah. So the A of G is the adjacency matrix of a graph. So now we have bilabeled graphs, and now we also have some operations on the bilabeled graphs. So the idea is that we will apply some operations on these bilabeled graphs to build our graph classes, and then we will have a corresponding operations on the matrices that will, so let's just see. So for example, this is the series composition operation. So you have one graph, and you have these output wires in here, and here you have another graph, and you have these input wires in this other graph. So the series composition is basically just connect the first wire here to the first wire here, the second wire here to the second wire here, and so on. Get rid of, so sort of connect them, and so identify this vertex here with this, and get rid of the multiple edges. So here is a more concrete example. So if you take a graph like this, you series compose them, then you get something like this. And the corresponding matrix operation. So if we take a graph and bilabeled graphs and series compose them, then the corresponding matrix, homomorphism counting matrix of the composition will be product of those two matrices. And this is how we can then keep track of the homomorphisms. We will be doing some operations on the graphs, and we know how to keep track of the homomorphisms by doing some operations on the matrices. So we just multiply the matrices and we get all the homomorphism counts. Another operation that we have is the parallel composition. So in terms of these bilabeled graphs, you can just imagine like putting those graphs on top of each other. So for example, here you have this matching, and here you have a cycle. And if you put them on top of each other, then you get this ladder. And the corresponding matrix, homomorphism counting matrix, will be the entry-wise product of the matrices. Right, so these are two main operations that we use. There are more of the operations on bilabeled graphs that are used in the literature, but these are the two main that we need here. And then there are some other operations which are slightly technical, for example. So, for example, transposition, it's just in terms of graphs, you flip the wires. And in terms of matrices, you do a transposition. And then there is a cyclic permutation, which you sort of, in graphs, you cyclically permute the wires. And there is also a corresponding matrix operation. So it's not clear why these are necessary, but sort of are. I would say that's a bit of a technicality. Okay, so now we are ready to define the class PK. And so first we define the atomic graphs. So this will be the class QK. So the atomic graphs are the set of all minors of the cycle and the set of all minors of the matching. What does that mean? So minor means like whatever you can get from the graph by deleting edges, vertices, and contracting edges. So that's a minor. So here we have the matching. This is the matching MK, and this is the cycle CK. So the atomic graphs here are the minors of this and minors of this. So this is here, and all the atomic graphs will be the union of this. We need to split it for a reason which will be apparent soon. So then the class PK is the set of all KK bilabeled graphs generated by the elements of this QK under series composition, parallel composition, but only with the elements of this first one. So you are only allowed to do parallel composition with the minors of a cycle. The reason is planarity. So we want to preserve the planarity, and that's roughly the reason. Then you can do a transposition, and then you can do these cyclic permutations. And then finally you get a class PK without a boldface. You just remove the labels. You just remove the labels. So this is the class PK. Whatever can be generated from these atomic graphs using these operations. And now you keep track of. So for this basic atomic graphs, we know what are the homomorphism counting matrices, and now you can keep track of all the homomorphisms by what I explained, that when you apply an operation on graphs, you know what the corresponding operations on matrices is. So what have we actually done is that QKG with a hat is a minimal matrix algebra over complex numbers that contains all the homomorphism matrices of all atomic graphs. So it's unital, it's self-adjoint. So this is a theorem, this is not maybe obvious. So it's unital, it's self-adjoint, it contains the matrix J, which is all ones matrix, like every entry has one. It's closed under the cyclic permutations of labels. It's closed under the Schur product, which is the entry-wise product, and it's it's closed under entry-wise product only with this atomic graphs QKP. And of course, it's an algebra, so in that it's also, of course, closed under matrix multiplication and so on. So the theorem is that these graphs are homomorphism indistinguishable over the class of graphs PK, which we defined, if and only if there is an isomorphism between the okay, so here should be a G. If and only if there is, H, if and only if there is an isomorphism between the corresponding matrix algebras. So, okay, so yeah, if you have seen something like, for example, Weisser-Lehmann algorithm, which also constructs some kind of matrix algebra over a graph, this is kind of similar to that, I would say. That and what we want to do next. So next, we apply the MPA hierarchy to this GH isomorphism game and get a relaxation of quantum isomorphism for each natural number. And then the feasibility of the, so this kth level is some kind of semi-definite program, and the feasibility of this kth level will give us this okay, here should be again H. So this feasibility of this semi-definite program on the kth level will give us the algebra isomorphism here. And on the other hand, we also will do the other direction. So if we have the isomorphism, we can show that this will be feasible. So I have the definition of the MPA hierarchy at the end, like formal, but I don't think it's necessary to do this formally, just intuitively. So let's see what is the intuition behind the MPA hierarchy. So the idea is that this you have this commuting operator strategies that I defined for the graph isomorphism game, but of course you can have it for any kind of game, for any kind of commuting operator strategy, for any kind of non-local game. You can define this commuting operator strategy, and for a commuting operator strategy, you can define a series of semi-definite programs that converge to the value of the commuting operator value of the game. So the maximum winning probability. How is this done? Is like you consider basically this kind of vectors. So you take integer n, and then for every L that is at most k, so you define the following vector indexed by this kind of string of length 2L, and now these are the measurement operators in the strategy, and this is the shared vector of the players. And for all possible such combinations, you take vectors like this, and then you take the gram matrix of these vectors, and this will be a positive semi-definite matrix, like whose entries will satisfy some linear constraints, and this will give rise to a semi-definite program, which gives rise to the MPA hierarchy. So here is just an illustration. I don't want to go into the technicalities of this, but this is just like a visual thing to see, like how there are some conditions and so on. So okay, so what do we need is that some matrix R, a complex matrix R, which is indexed by strings of length at most k, or 2k, where this alphabet is the vertices of the two graphs. So the certificate for the kth level is some matrix that satisfies some conditions. It's in particular is positive semi-definite, and it satisfies some additional conditions. And one of the conditions is actually encodes sort of like the winning condition for the game. And so what do we actually need here? Just is that the GH isomorphism game has a perfect quantum strategy. I quantum strategy, I mean this commuting operator strategy, if and only if there exists such matrix for every k, for every level of the NPA hierarchy. And okay, so now we want to extract this isomorphism of algebras, and for that we make use of choice theorem. So what is choice theorem? So it's a very neat result from linear algebra. So a map between matrix algebras is called positive. By positive I mean positive semi-definite. If this image if it basically maps positive semi-definite matrices to positive semi-definite matrices, and it's called completely positive if for all R, if you tensor the map with the identity of size R, for all R, it should be positive. And the Choi matrix of a linear map between the matrix algebras is this kind of matrix. So it's some kind of matrix associated to the linear map, and so this matrix Eij denotes just a matrix which is 1 at the ijth entry and 0 otherwise. And the very influential theorem of Choi, which is like a very short paper with thousands of citations, because these completely positive maps appear a lot in quantum information. So is that you can characterize positive maps using this matrix. So this is like a test for a map being completely positive, is that a map is completely positive if and only if this associated Choi matrix is positive. And so now how do we, so we construct a completely positive map. So we take, so we have this MPA hierarchy. The feasibility of the MPA hierarchy gives us some certificate, this matrix R, which satisfies certain conditions. And so what do we do is like let R be the solution for the kth level of this MPA hierarchy, and we take C to be a principal submatrix of R, which is indexed by this kind of set. So remember that this matrix R, this certificate for the kth level of MPA hierarchy, is a much larger matrix. So it is indexed by all strings of length at most k over this alphabet. But this is a principal submatrix corresponding to the strings corresponding to the strings of length exactly k. So it's some kind of submatrix of the certificate for the semi-definite programs. And now, so we define a linear map between matrix algebras. So this Vj to the k. So this is like what we will want, right? So we want some kind of map between matrix algebras. And so we use this principal submatrix to define this linear map in the way that we say that, okay, let's take the map which has this principal submatrix as a Choi matrix. So remember that the Choi matrix is some map associated to a linear map. So we sort of are using this choice theorem in the other direction in some sense, right? So we are taking a matrix and defining a linear map which has this matrix as a choice matrix. So we will know that, so this matrix will be positive because it's actually coming from a positive semi-definite matrix, which is a certificate for the MPA hierarchy. And so we already know that it's positive. And so this will define as a completely positive map by this theorem. So we are taking a positive matrix and we are defining a linear map which has this matrix as a choice matrix. And actually the constraints from the MPA hierarchy on this certificate would translate into constraints on this map phi that we define like this. So it turns out that if we define a map like this from this certificate, we get what we then call a level K quantum isomorphism map, which is basically just a map between the matrix algebras that satisfies all these conditions that I before mentioned. So here they just listed that it should satisfy as an isomorphism of these matrix algebras that we constructed using these bilabeled graphs. So it's just it's unital and it preserves the J matrix and it works well with the entry-wise product, and it's of course matrix algebra. It's a linear map, so between matrix algebra, so it will of course work well with the product of matrices, and yeah, and this thing that it will take the homomorphism counting matrix of the graph G to the homomorphism counting matrix of the graph H. And the existence of such map implies, as I already mentioned, the homomorphism indistinguishability over PK. And yeah, with some additional combinatorics, we can get the other direction. Okay, so this is kind of like a summary of what was done, is that we have this kth level of the MPA hierarchy, which is feasible. So this means that there exists this big positive semi-definite matrix that certifies the feasibility. And this is equivalent to the existence of level K quantum isomorphism map, which is just this map, this special kind of map between these matrix algebras that we constructed using the bilabeled graphs. And this is equivalent to homomorphism indistinguishability over PK, which intuitively follows from how we were constructing these bilabeled graphs. Because we record all the homomorphisms in the homomorphism counting matrices, in the matrix algebras. And so we also finally recover the Manchinska-Robertson result, so which basically says that two graphs are quantum isomorphic if and only if they are homomorphism indistinguishable over all planar graphs. So, so this is just a corollary, right? So we get, so this P is just a union of all PK. And to actually recover the Robertson and Manchinska result, we somehow need to prove that this union of our PK classes already contains all planar graphs. So yes, so it's left to somehow see that this P contains all planar graphs. And of course, this union of our classes will be a subset of planar graphs because everything is planar and all these operations preserve planarity. And now here for the other inclusion, we sort of need some combinatorial results. So, which is basically just that intuitively every planar graph is subgraph or a minor of some grid. You can imagine this, that you basically, I mean, it's not hard to imagine, but it's not that easy to prove, but it's not hard to imagine that you can basically draw any planar graph in a sufficiently large grid. So all we need to do that is to show that actually our classes will contain the grids, and which is true because we can do these ladders, and then using series composition we can also do grids. So actually the class pk will contain a k times k grid. So we will get all the planar graphs. So it is well known that every planar graph is a minor of some grid. So since we can generate all the grids, we will also get all the planar graphs. So our classes are minor closed. So that's okay. Yes, and that's the end. And here are just some remarks at the end. So okay, so yeah, maybe just some remarks about. So we can get some algorithm determining whether two graphs are homomorphism indistinguishable over pk. So as I mentioned, this is undecidable problem quantum isomorphism for each level k. We can get an algorithm which runs in polynomial time, and maybe a question would be like whether we can get some better description of these classes, but probably that's a hard question. I mean, we already can describe them by some generators. Like, for example, if k is equal to 1, this P1 class would be this so-called outer planar graph, where you can draw a graph so that all the vertices are on the outer face. So for example, for k equals 1, we have some nice description, but for the other k we don't. But I guess that's it.
Thank you very much for the nice talk. Do we have any questions, comments, concerns?
Yes, concern?
Yes, so I have a question. So you had these bi-labeled graphs, and there were like two products, right? There was this circle product, and the other one was the component-wise product.
Yeah, like the regular, like a series product, which corresponds to the matrix multiplication, and the parallel composition, which corresponds to the entry-wise product of the matrices.
Right. So my question is, so how do these products interact? So is it like associative if I first do the first and then the second? Is it the same as other way around, or do they form some duoidal category? Or
well, it's yeah, I don't know. I mean, we were only concerned like you can apply them in any kind of order. So like everything that that belongs into the class, it doesn't matter what is the sequence of the operations that you apply. But I'm not sure about the exact interaction of this. Yeah.
Okay.
So maybe to follow up on that, I got the impression that in the original proof by Manchinska and Robertson, these bi-labeled graphs come up as like they come somehow from the representation theory of the quantum symmetric group, or they're closely related to these string diagrams that they have in. So do you know more about that than I do, or?
I think we know about the same.
Yeah. So then I'll maybe turn it into a comment. So my understanding is that the reason why you get these planar graphs for quantum isomorphism is somehow when you build these bi-labeled graphs, but so they will correspond somehow to intertwiners of the quantum automorphism group, and like just my very basic high-level understanding is that the planarity comes from the non-commutativity, that you're not allowed to cross edges anymore, and that's why you only get planar graphs. But that's just like a very high-level idea of why planar graphs come up here. I think maybe I should ask David or Laura, they can
Okay.
maybe say more about this.
Yeah, here it was somehow simpler because we sort of like already knew what the result should be. So
Yeah, and just to be sure, there were no quantum groups or tensor categories in your proof, right?
absolutely not, just
Yeah.
elementary linear algebra.
Yeah. Thank you.
So maybe another question related to this. Can you go back to the definition of this homomorphism,
Well,
indistinguishability?
to the beginning, right? So
what if you use instead of planar graphs, so graphs that you can draw on higher?
yeah, that's a good question. We are thinking about it.
Okay.
But yeah, so it's absolutely not clear what is the corresponding thing. But yeah, we're thinking about it, and it would be really nice. So there is this conjecture. Maybe Jose will remember it. So like, what is the David's conjecture in the Homomorphism paper? So like homomorphism indistinguishability closed, minor closed. Right, so like the decidability versus undecidability. I now don't remember exactly the conditions, like, but like the interesting question is like basically when is this homomorphism indistinguishability, when it's decidable algorithmically and when it's undecidable.
Well, is there something between planar graphs and whole graphs where it is decidable?
So like, so the planar graphs are now the main example of this, where so satisfying these conditions that we do not remember exactly, that that is undecidable. And I mean, it would be, for example, nice to prove that if you replace planar graphs by bounded genus, like something that you can draw on a torus with some holes. Sorry, like at most k genus surface, right? Orientable, for example, then like a word, like whether it should be undecidable according to the conjecture, it should be undecidable, and for example, it would be nice to prove that.
So I may have missed it at the very start, but is this just for finite graphs, or is this completely?
Yeah, just finite.
Okay. And so I'm guessing it's already hard to formulate anything similar for infinite graphs, because
yeah, I don't
imagine the original
infinite graphs, so I don't know.
Yeah,
I really don't know much about infinite graphs, so
I imagine already like the original theorem of Lovach might fail for graphs.
Yeah, I really don't know about infinite graphs. So.
Yeah. Okay.
The only thing I know about infinite graphs is that quantum automorphism groups of infinite graphs have been studied a bit. But there you already run into all sorts of problems for getting a compact quantum group. So I think it will be locally compact if you assume that the graph is locally finite, meaning that every vertex has finite degree. Then Christian Vogt has done some work on like defining quantum permutation matrices of infinite sets where you don't assume this local finiteness, and you can still do something, but you only get the quantum permutation matrices. There's no quantum group structure that we can discern anymore, or maybe it's a discrete quantum group or something. But in terms of isomorphisms, so also in quantum information theory, people don't typically study, say, non-local games with infinite input and output sets, because in quantum information, everything is typically finite. So I don't think this is something that a lot of people care about in that sense. But of course, as a graph theorist, this is a very interesting question. But yeah, let's say it's open for us to work on. No.
Just a question about the quantum automorphism group. So if I understood correctly, these things are going to be compact quantum groups in the sense of Ardanovich. Yeah. So is there some, I'm very interested in quantum subgroups, so that's going to be another Hopf algebra or another compact quantum group together with a surjective map. Is it naive to expect that quantum subgroups might correspond in some sense to subgraphs?
So
I'd like to construct quantum subgroups, which is to say I'd have your compact quantum group and then you got a surjective Hopf algebra or compact quantum group algebra map onto the guy downstairs. Is there some way to construct this around the graph? I mean, a naive idea is that it'd be subgraphs, sorry.
yeah,
To get a grip on the homomorphism group, we ask callers to either the vertices or the axes or both. And then you look at the subgroup of only those quantum permutations, maybe
Yeah. And so
This way you can first find the stabilizer of the vertex. Or the vertex differently.
Yeah. Ultimately, you're taking spaces of covariance of these things, you would get quantum homogeneous spaces somehow. I mean, everything is semi-simple, so this should work. If you have a quantum subgroup, you win. Yeah, because everything is a compact quantum group, so it will work. And then another question is like about the Hopf algebra inside in these compact quantum groups. If you look at the Joule Hopf algebra, can you say anything about how many primitive elements are in there or what this thing means in general?
yeah.
It's a very specific question.
Afterwards, I don't know.
Yeah.
So my understanding goes up to compact matrix quantum groups. So I don't know really.
It's just because these things look like matrix groups very much, obviously.
Yeah.
So then, dually, you should have something in the Hopf algebra since it looks like a universal enveloping.
Yeah, so our knowledge is pretty much limited to these or graphs.
But maybe it's, we can discuss it somehow.
Are related to like locally compact.
Yeah.
quantum group sets of graphs.
It's like the algebraic version. I have a definition. I'm looking for examples. You guys might have some.
Yeah, we certainly might have some when we understand the definition.
Okay. Can I ask?
And realize every finite group as the automorphism group of a finite graph. Now we know that you cannot get every finite quantum group. Finite graph because
So to get a Frooks theorem, you have to go to quantum graphs, I think. Like there has been recently some research.
This is what like J.P. McCarthy and Theo Banneker were looking at. Yeah.
Which groups for the quantum groups do have good property, and some of them that in study are rules of finite groups.
Okay.
So we know for some specific finite groups that they are not possible to realize. That's a really specific example. So what can be in our construction of asymmetric graphs with quantum symmetry? And then we get a graph quantum homomorphic group is dual of the alternating group T8. And there we can like construct graphs with specific dual finite. That's it. This provides your.
I'm not sure, but okay, thank you very much. Can I ask one very quick question? If we go back to there was the game with Alice and Bob where they had to convince the referee. If they do convince the referee, does that mean their article gets accepted?
Sorry? Okay. Yeah, I wish.
We could have covered a project that for asymmetric graphs with quantum symmetry, it would be had to be quantum.
Yeah.
And also invite everyone to a seminar. Great and good.